Hi. In this video, what we're going to do is we're going to look at some qualitative aspects of entropy. We're going to look specifically at the effect of temperature changes and volume changes for entropy. Okay, so this is section 17.3. So 17.3, and we're going to talk about entropy some more. Okay. So again, the idea of entropy is that it's a measure of really the variety of possible states that energy can exist. So the greater the number of states that are possible, the greater the entropy. So if we have molecules that are confined to a small space, like a solid, right? Then we would say that it has a pretty small amount of entropy. Now, if we vaporize the solid into a gas, now the possible states are very large, right? The arrangement is quite variable now. So that would be an increase in entropy. Entropy would increase in that case. And when we say that entropy increases, really what we're looking at is what's called delta S, the change in entropy, right? And that would be equal to the final entropy minus the initial, okay? So if the entropy increases, we would say that delta S is greater than 0. It's positive, right? 10 to 20. 20 minus 10 is positive 10. That's an increase. On the other hand, if we were to do the opposite, if we were to condense a solid back into a liquid or a gas, I'm sorry, liquid or a solid, so we're going from a gas down to a solid, then that would be a decrease in entropy because we would be reducing the number of possible states. So entropy, when that decreases, delta S is less than 0. Okay, it's a negative change. Okay, so what we're going to do is we're going to look at the effect of volume and temperature in the next problem. And so, less volume, less entropy. More volume, more entropy. It's a pretty simple relationship. Now, there's also a relationship with temperature. And so what happens is, as we increase the temperature of molecules, they will start to, the term used is populate. They will start to populate different energy levels. So there may be a type of rotation or a type of vibration that occurs in a molecule that at low temperature doesn't really exist. There's not enough energy to excite that molecule into vibrating in the now, like that, right? But if I put in energy, then what can happen is we can excite that molecule into a new type of motion, a new type of vibration or rotation, translation, electronic even, right? So there is a tendency then, as the temperature increases, for the energy to be distributed into the molecules. So the molecules will now have more disorder, a greater amount of entropy. So the effect of temperature tends to be greater temperature, more entropy, lower temperature, less entropy. Okay, so those are the two relationships in this problem. So what I'm going to do is I'm going to pull up one of these Alex problems and let's take a look. Predicting qualitatively how entropy changes with temperature and volume. For each system listed in the first column of the table below, decide if possible whether the change described in the second column will increase the entropy S of the system, decrease entropy or decrease S, or leave S unchanged. If you don't have enough information to decide, check the not enough information button in the last column. Okay, so let's take a look at the first one. The first one is the system. So that's what we're studying, is a few grams of ammonia vapor. So it's ammonia gas, right? So these are gaseous molecules bouncing around in a container. The ammonia condenses to a liquid at a constant temperature of -2°C. So constant temperature, that's telling us the temperature is not changing. So we're not going to see any change in entropy due to temperature changes because there are no temperature changes. However, what happens when a gas is converted into a liquid? It condenses down to a much lower volume. If we condense down to a much lower volume, that reduces the number of possible states of the molecules, so we're going to see a reduction in entropy. A reduction of entropy is a change of entropy that's less than 0. So we would select the delta S is less than 0, change which is negative. In the second one, we see a few moles of carbon dioxide gas. Okay, so a little more than a few grams of ammonia vapor. Now we have a few moles of carbon dioxide. In the gas phase, the carbon dioxide is compressed from a volume 11.0 liters to a volume of 2.0 liters, while the temperature is held constant at 1.0 degrees Celsius. So again, the temperature is constant in this problem. So we're not going to see any change in entropy due to temperature changes. However, the volume is changing. In this case, we're compressing it, right? We're moving it down to a smaller volume. Fewer possible states of the molecules. They're now being ordered. You imagine if you push and push and push, eventually it'll solidify, and now it has very little disorder, right? So now it's a very ordered material. Crystals are very ordered, highly ordered materials. So a reduction of volume is, again, a reduction in the entropy. Delta S would be negative, right? So less than 0. In the third one, a few moles of carbon dioxide gas again. The carbon dioxide is cooled from 50.0 degrees Celsius to 9.0 degrees Celsius and is also compressed from a volume of 15.0 liters down to a volume of 9.0 liters. Again, it's being compressed to a smaller volume. Smaller volume is fewer possible states, a reduction of entropy. So again, delta S would be less than 0. Okay, so to sum it up, we have two phenomena we're looking at here in terms of entropy: the effect of temperature changes and the effect of volume changes. In this particular case, we were really just looking at volume changes, right? In this case, it's all volume changes.